We've got 4 identical bulbs. They're connected in the circuit as shown. In comparison with bulb 3, what do we know about bulb 4? Let's first think about this. This is a series circuit. So this is my main branch over here. And then I will have a choice there to go either that way or that way. And I can do the same thing over there. So what I see quite clearly is on this branch, I've only got 1 light bulb, whilst on this branch, I've got 2 light bulbs. The potential difference across branches, you know, is going to be, if we're going to call that X, then this potential difference between blue and pink would also be, we can't use X because it looks like a light bulb then, so we'll just call it V. This will have the identical potential difference. What that means is that 4 will have half of that potential difference. So that'll be a half V, and then this one will have a half V, and in total it would be equal to V. So the potential difference on bulb 4 in comparison with bulb 3, bulb 4 has got less potential difference. Also, bulb 4 it's going to be much more difficult for current to go in that branch than in this branch. So the current is going to be lazy. More current will go the easy route, and less current will go the hard route. So if there's less current in 2 and 4, those bulbs are also going to be less bright. So your correct answer is A. In the circuit over here, we are given identical resistors, and their internal battery resistance of the battery we ignore. Switch S is initially closed, and when we open switch S, the resistance of the circuit will do what, and the ammeter will do what. The minute I take this branch away, I am making the circuit more difficult. Therefore, the resistance of the whole circuit increases, and because of that, we are going to find that the ammeter reading is going to decrease. So the resistance will increase and the ammeter reading will decrease. We've got a circuit over here. The switch is closed and the internal resistance is negligible, thank goodness, because we haven't learnt about it yet. How will the ammeter and the voltmeter readings change if I open that switch? And it's the same concept. As I take away that branch, the circuit becomes more difficult. So the resistance goes up. What does that do to the ammeter reading? The ammeter reading is going to come down. So your ammeter reading is going to decrease. In this circuit, there's only one place to spend your money. So it doesn't matter whether it was split or whether it wasn't. Your voltmeter has to stay the same because you had, let's say, 10 Rand to leave home with before, and you still only have 10 Rand to leave home with. So there's no change on the voltmeter reading. You've got 3 resistors shown in the section of the circuit. They are identical. How do the potential differences compare? Now, if they're identical, we would have a potential difference, or let's go this way rather, over there, which would be the same as the potential difference over there, which would be the same as, that's half of V, and sorry, this is very difficult to draw in this small space, maybe I should make it bigger, and here again, we have got half of V. So those two add up to V. And the question is, how do the resistors compare? Well, X's V is equal to Y's V, which happens to be equal to half of Z's V. Let's see if we can find the right answer in the ones that are given. So it does say that Vx and Vy, and this seems like a true enough statement. Let's see if we can get a better one, maybe with the half in there. They definitely aren't all equal to each other. Vx is half of Vz, not double it, and there's no quarters of any sort at all here. So the correct answer is going to be A. 2 identical resistors are connected in parallel as shown below. The resistance of the cell and the conducting wires can be ignored. Sorry, this poor picture is starting to look a little bit tired. I don't know. Maybe we can beef it up a little bit. There we go. Okay, so you've got the circuit over here. When the switch is closed, what will happen? So the switch is closed means I'm going to add a resistor in parallel. The minute I add a resistor in parallel, what's going to happen to this ammeter reading is that the current coming along is going to now have to split. But at the same time, we need to consider what is going on over here. So let's say this was 2 volts. And let's say that this reading over here was 2 amps. I'm going to use 3 amps rather, because 2 and 2 just seem to make too many convenient numbers. So this resistor over here is therefore going to be, R is going to be V over I, which is going to be 3 over 2, which is 1,5. And this was now 1,5 as well. So let's see what happens to my resistance. I've got 1 over R parallel is equal to 1 over 1,5 plus 1 over 1,5, which is equal to 2 over 1,5, which is therefore going to be equal to 1,5 divided by 2, which is 0,75. I then say, what is going to, my potential difference has not changed, so let's see what happens on this branch over here with the current. So the current is now equal to the potential difference, which has not changed, 2 volts, divided by my new 0,75, my new current strength. And what I find out is that I land up with exactly, once again, 3 amps. So it is going to remain unchanged. Sometimes it is best to use numbers to be able to get these answers to be worked out. Here we've got a circuit that represents, in the circuit represented by the following circuit diagram, R1 has got double the resistance of R2. What is the relationships of the currents? Now, R1 is twice as difficult. That means half as much current will go there and double the amount of current will go over there. So in other words, I2 is equal to twice I1, because I have landed up with half as much current going in this direction over here, because this was twice as difficult. So it's 2 times a half, and this one's only going to be equal to, that one's got a resistance of that, of 1 ohm, let's say. Let's just pretend for a second. R1 is double R2, and therefore if I had half amp going up to the top, I would land up with 1 amp going down to the bottom. How do I know that? Because I need to be able to get a voltmeter reading over here that is exactly equal to a voltmeter reading over there. So half times 2 is 1 volt, and 1 times 1 is also 1 volt. So I am going to have I2 being equal to twice whatever I1 is equal to. What does that mean? That means that actually I1 is half of I2. Which means that my correct answer is actually A. Sorry about that. If the battery voltage is 18 volts, what is the voltage of each cell? So I'm going to just go through this quickly and rather work out the answers afterwards. So if it's 3 volts, at least 18 volts, this must be 6 volts each. Calculate the reading on V1. So V1 is going to be equal to, V is equal to I times R, which is equal to 1,5 times by 4. So that is equal to 6 volts. So this is now 6. Calculate the reading on V2. 6 volts got spent at dinner, so I left home with 18 Rand, 6 Rand got spent at dinner. I've therefore got 12 Rand left to spend at V2. Calculate the reading on ammeter number 2. Ammeter number 2 is going through this branch over here, so I is equal to V divided by R, which is going to be equal to 12 divided by 12, and therefore I'll end up with 1 amp over here. 1,5 amp comes along. The reading on A3 is going to be 0,5 amps, because 1 plus 0,5, one person goes to the top movie, half a person goes to the bottom movie if 1.5 people were going to the movies. Obviously you can't have 1.5 people, but just stay with the program on this. So that's going to land up being that. And calculate the reading on voltmeter number 3. So now you're going to say V is equal to I times R. If I'm looking specifically at voltmeter number 3, the current is 0,5, and the resistance of that resistor is 16, so it's going to land up being 8 volts.